welcome to this extraordinary course of Siegman. Thank you to the whole art team that gave us a lot today. And we are honored to have Anthony Siegman here today. I have a on paper, I do a role here to introduce it. But Tony studied in Harvard, UCLA, and the PhD at Stanford. And he became a professor then in 1956 at Stanford. So, and he was also a chair professor there. He got multiple awards. I believe the latest is the Esther Hoffman Medal Award of the USA. And he was also a Officer Society of American President in 1999. So we saw his column in the OPM for a year, right? And he's a member of the National Academy of Sciences and National Academy of Engineering, which is the company. So, and most of you might know him through his books on lasers. And so, this how to have
Well, thank you very much, and I'm very glad to be here and see at least a few old acquaintances. Dave Anderson and a former fellow student, Frank Barnes, who I guess he's not today for his talk, but was interested at the same time. Look, this is going to be an informal talk and a bit confused, muddied a bit. Also, I had the dreaded computer hard disk failure this morning, so this is my laptop is running off a backup and on an external drive, and I think it's going to work. But that imposed a little stress in trying to get ready for this. This year is the 50th anniversary of the invention of the first laser, operation of the first laser, as you see in the picture here. And so I think some of you will know there's been a program going on all year of events and talks and publications and a website and so on called Laser Fest. And just go to www.laserfest.org and look at what's there. And I was not a laser pioneer in any sense, but I was very fortunate as a very young faculty member to be in the maser business and to be around when the laser got started and to know quite a few of the people. And so I've become, to a certain extent, the guru on laser history, and I've spent more time than I probably should have this year on giving talks about how the laser came to be in the laser history. And that's not what I'm going to talk about today. But I thought I might just start off with the first two slides on it, because there's some connection to Colorado as well. So this is not exactly the exact design of the very first laser. You can see that in just a second. But it's the essential elements: a spiral flash lamp, a ruby rod, and a brilliant pulsed, very high power beam, which when focused down would give you air breakdown and drill through razor blades and so on. At this point, I'm not really sure whether I ever directly met Ted Maidman, but we were both graduate students, and in about the middle of the 1950s. But he had been, and before that, an undergraduate at Colorado State, and not a particularly distinguished academic record, apparently, as a matter of fact. And he then took a job and decided that wasn't what he wanted to do. He wanted to do some real inventing and real science, and he wanted to get into the Stanford Physics Department, which was very exclusive. And they turned him down 3 times. And finally, at some point in the early 1950s, he hitchhiked across the country from where he was working on the East Coast and showed up in the Stanford Double E department office, and we had I would have been, I still was 2 years from coming to Stanford at that point, but we had Stanford had a large sort of 200 master's degrees a year program, and so he had a somewhat more open admission standard. And he managed to talk the Double E department into admitting him for a master's degree, which he got within a year with a very good record. And but then he went over to the physics department, and Willis Lamb, subsequently to become a Nobel laureate, spent 2 years in the late 1950s or the middle 1950s at Stanford as a very junior faculty member before going on to Oxford and ultimately Yale. And Ted Maiman managed to talk Willis Lamb into taking him on as a PhD student. Lamb, he pressed very hard, and apparently Lamb told him he'd give him a 3-month trial period, and Lamb was working on the measurements of the Lamb shift and the very sophisticated spectroscopy, for which he got a Nobel Prize just a few years later. And I think he realized that Ted Maiman both knew a lot of physics and knew a lot of electronics. Maybe Willis Lamb didn't know what a phase-sensitive detector was, and Ted Maiman did. Anyway, within 2 weeks he took him on, and Maiman did a very good, very sophisticated, published in Phys Rev thesis with Lamb, went around the world for a year. Then went to Hughes Research Labs, which was in Culver City at the time, and was assigned to make microwave masers as low noise amplifiers on the military program. And over the objections of his bosses at Hughes, started working on calculations and so on to make this laser. So I'm required by the terms of my retirement program at Stanford to mention to you that the laser was invented by a Stanford EE and physics graduate. And this first work, just days after Hughes Research Labs moved into a glamorous hillside laboratory, which sits up above looking out on the beaches in Malibu, and the lab is still there. It's now called HRL, and the room in which he the first laser is still there. So let me make sure I can go ahead here on the slide. Yeah. So these are Ted Maiman's hands, and this is actually the essentially the first laser that he ever made. And its utter simplicity, as you see here, this short, stubby rod and an enclosure and this flash lamp belie the sophistication of the physics that he put in. Arthur Schollo and others thought that the quantum efficiency of the fluorescence in ruby was only in the few percent range, and it would never, besides that, it was a 3-level laser, and it would never work, and they had given up on it. Ted did very sophisticated quantum fluorescence, quantum efficiency measurements, and other measurements, which led to several Phys Rev papers, and calculated with a bright enough, just at the margin of the brightest arc lamp that he could obtain, he might just barely be able to make it blaze. It's that the mirrors were just silver coatings on the end. And then the breakthrough was the idea that this was a spiral flash lamp. When you get your picture taken, there are often 2 lamps sitting up there that flash, or when you see flashing lamps on obstacles on the road, there's xenon flash lamps like this. They could be bought off the shelf. You bought one of those lamps and made this device. And my understanding is it worked the first time they fired it. And they weren't even sure that it worked, because nobody had looked at a laser beam before, and especially a pulse laser beam, and they didn't almost know what to look look for. But so that's the story of how the first laser came to be. And then there were a series of really weird publishing. He sent off a paper on this to Fisher Letters, I think it was. There had been a flood of earlier microwave, and he called this an optical maser, which was what it was called at the time. And Samuel Goudsmith, a distinguished physicist who was the editor of Fisher Letters, had said, we published all the maser papers we were going to ever publish that new coming along, and he flatly turned it down, turned the paper down, and without even refereeing it, and then complicated things, and so Mayman, between all these things, basically once he had done this, left basic science and went into industry and became the director of a major research laboratory and so on, and did not do any scientific publishing beyond that, and never got, due to various circumstances, never got a Nobel Prize for this. Well, what I want to talk about today, partly because of these computer breakdowns, and I hadn't been sure I was giving a seminar here. I hadn't been quite prepared, but I gave a paper in a Laser Fest session in Denver at the IEEE Photonics Society. The first speaker was Tingy Lee of the Fox and Lee, who some of you will know made the first resonator calculations by doing iterative bouncing back and forth of a wave between two mirrors and finding that indeed modes did develop. And I hadn't realized until hearing from Tingy yesterday that they actually did these calculations before the first maser actually operated. People just thought, well, we're going to put up two flat mirrors and get them very carefully aligned and make a fabric row, and somehow that will serve as a cavity. And the other people said these cavities would not have modes because they were the cavity operators and non-Hermitian operator, the optical. And so Tingy talked about how this came about, and then I gave a kind of a historical review of all the developments, immense developments in laser cavities, laser resonators of all different kinds, and optics that have evolved since the laser came along. And so just very quickly, the laser brought up to popular attention a lot of important and also a lot of obscure optical effects that had been known in the late 1800s, in the time of Rayleigh and Maxwell and the kind of giants of electromagnetic theory of that era. And one of the interesting ones was this Gouy phase shift, which Professor Gouy in Paris actually discovered experimentally, or I guess he must have realized that it would happen, or it probably happened, and confirmed it experimentally. If you put a beam through a focus, any beam through a focus like this, a reasonably uniform beam or Gaussian beam or whatever, and you do something to measure the phase velocity or to look at where the phase fronts, how far apart they are going through the focus. This Gouy phase shift is the fact that you find that you have an added pi phase shift just from going through the focal region. And that demonstrates that you have a large transverse derivatives here. So when you do del squared plus k squared for the propagation, the del squared term has some large transverse terms, and that makes the phase propagation different. And it turns out to be exactly an integrated shift of pi going through this. So he set up a point source and bounced it off two mirrors, one to make a collimated beam, one to make a converging beam, he looked at the circular interference fringes down in the focal region here, and I think any of you who've done interferometry can appreciate how difficult this would have been to do with an incoherent source like this. And he found that if the fringes had a bright spot in the center on one side, they had a dark spot on the other. That was this 180-degree phase shift. The plane wave and the total accumulated phase shift of the spherical wave differed by exactly pi in going through the focus. And this turns out to be important for laser modes and for transverse mode beats and lasers and things like this. So I learned this from someone, and I wrote it up, and those of you who have my lasers book will recognize that these figures are from the lasers. This is a couple of figures from chapter 17 of the monster book, and you know, my only problem was that, I don't know, I guess I didn't know any French, and somehow I thought Goy was more French than Goy, and so if you check, you'll find that I misspelled Goy, and I got a fast word processor and made a count, and I misspelled it 47 times. And we don't want riots. The French are worried about their language, and we don't want riots in Paris over this. And so we'll go through and correct this. So that's just one example of old optics coming up and becoming important when you have a coherent optic source like the laser. Now, another thing, and I've got 3 of these things to show you. One of them, the last one's somewhat longer. You all know Huygens integral, and you propagate a field from one plane to another by doing an integral over a Huygens kernel here, or a Sommerfeld version of that kernel. But sometimes you want to go through a bunch of optical elements, lenses, Gaussian ducts, other stuff in between here, and not just free space, but maybe some free space lengths. And you can write a ray matrix, a so-called ABCD matrix, which translates the position and slope at the input to the position and slope at the output. And if you send a beam through this, and you make, these elements are either large enough or the beam is confined enough that you don't run into edge diffraction effects at the edges of the elements, it turns out that you can write Huygens integral through a whole cascaded arbitrary set of elements just by knowing the cascaded ABCD matrix through this cascade of elements. And so the Huygens kernel just depends on the A, B, and D elements, and the C doesn't show up here because AD minus BC is 1, and so you can get rid of that. And this was a guy named Stu Collins, who was a professor of physics at the University of Ohio, who discovered this in 1970. And it just makes life a lot easier. You don't have to propagate here, multiply by the element, propagate, and so on. And you'll also notice that this kernel is basically parabolic. It has x squared, x squared, x1, x2, and x2 squared. And so it's a Gaussian type integral, and those integrals can be done. And you can actually handle so-called complex valued things where you have gain, transverse gain variations, and that's what we're going to come to in a minute. Now, I've been going on at a great speed here, but let me pause for a second and see any questions on this, or any. If you have a question anytime, please just wave your hand, because I appreciate it's a diverse audience, and so we have a. Now, I'm going to do this one also pretty quickly. Those of you who do quantum mechanics know that the be-all and end-all of quantum mechanics are Hermitian operators. Every physical system, every physical observable is represented by the eigenvalues of a Hermitian operator. Every quantum system has a Hamiltonian that's a Hermitian operator. And if it's not Hermitian, it ain't real. Or at least it's not, largely not measurable. And, and also those of you who work on microwaves will know about things like having the orthogonal modes of a closed microwave cavity, the orthogonal modes of a metal waveguide, and with the Rayleigh-Ritz procedure and the expansion in eigenmodes and the total power flowing down the waveguide is the sum of the power in the mode. And you use box normalization for a lot of problems. And this is solid state physics also. But laser cavities are generally finite sized mirrors of one sort or another lined up facing each other. They're open systems that to some extent leak radiation out to infinity. And so you can't use box normalization. And in fact, the Huygens integral that I just showed you is not a Hermitian integral operator. It's a complex symmetric, but not Hermitian. So a lot of laser resonators are very close to Hermitian, but not exactly. And some laser resonators are quite different from Hermitian. And so they're basically non-orthogonal or non-normal. They're not guaranteed to have eigenmodes rigorously, although they do. Even if these eigenmodes exist, they're not orthogonal, they're biorthogonal to adjoint modes. And that destroys a lot of things. For instance, the procedure of second quantization, which leads to the basic concept of photons, gets very muddled. If the total energy of the Hamiltonian is not just the sum of simple harmonic oscillators. And so you get, and it turns out, it was eventually realized that the whole idea of the Einstein A and B coefficients being equal for the quantum mechanicists in the group, and that the Einstein A coefficient, the Einstein B coefficient is essentially the Einstein A coefficient is the Einstein B coefficient produced by one photon in the cavity. And this all is muddied and partially lost, and so there may be situations where you will run into the following idea. This is a sort of a classical version of this. Here's an unstable lens guide. That is, this is intended to be an iterated, periodic, unstable lens guide. It's unstable in the sense that the beam there's a diverging lens in each aperture, so the beam expands like this, and part of it is lost, so it's a leaky waveguide, if you like. But this does have very definite eigenmodes that you can calculate. They're essentially diverging spherical wave and cut off here, and you get some edge waves and a spherical wave going out here. And some of you may be mode matching into Gaussian cavities by putting a Gaussian beam matched in width and phase into it. And you can mode match into a non-normal lens guide like this. And all the input energy goes into the whatever mode you match into. And for example, if you match into the lowest order mode and you plot the intensity on the axis here, say the intensity at the midpoint of each of these periods, if you excite the lowest order or lowest loss mode, you have and you plot log versus the number of periods that you've gone through, you get a straight line for this. If you deliberately excite a higher order mode, that's a more lossy mode. It's generally a somewhat bigger mode, and these higher order eigenmodes decay away faster the distance. Okay, and again, you may regard this as obvious or be puzzled. I'd be glad to take the question either way. But okay, now, but suppose that instead I take the input signal beam that I'm putting into this periodic lens guide. This is the first aperture, second, and the rest of the apertures stretch on indefinitely. if I come in with a beam like this, I'm obviously exciting some mixture of the eigenmodes. But physically, the beam is going to compress down like this because it's focused inward. Although due to the effects of the mirrors, it's going to eventually start bending outward, and also due to the diffraction, it's going to start bending outward. So if I follow this beam far enough, I'm going to get back into, I'm going to have something that's starting to look like the modes of the system. And so now in this case, suppose I put this adjoint beam into a system like this, and you could actually do an experiment like this. In the first few, typically 5, 6, 7, 8 periods of the waveguide, there's very little loss because the beam is focused much smaller than the edges of the aperture. So the power on axis, let's say, if you measure it, is going to stay nearly the same for quite a few periods until this beam has diverged out and turned into something that's beginning to look more, that looks more like the blue lines. And so eventually, what we've excited here is a mixture of the eigenmodes, and actually with amplitudes greater than the beam you're putting in, than the power that you're putting into this. But if you send a trusted Gilla experimentalist out here to measure the power at various apertures out here, they're going to, and ask them what they're seeing, they're going to tell you, well, I'm seeing the lowest order mode, and it's decaying just as it should with distance. And these modes are eigenmodes, and so you can follow that eigenmode back, and you find that you've excited the lowest order eigenmode with much more power than you're putting in. And this is called adjoint coupling, and it's just kind of a weird property. It's one of the weird things that happens when you have non-orthogonal modes. And high power lasers use unstable optical resonators, and sometimes you want to injection lock a big, powerful laser oscillator with a weak injected signal. And the best way to inject it is to inject it as an adjoint beam. That's why it's called adjoint coupling. Now, the second thing that comes out here is, in the very earliest days, in 1958, in fact, Shalom and Towns in particular, thinking about lasers and how they might be, would it be possible to make an optical maser instead of just a microwave maser, and how would you do this? Wrote a very scholarly, definitive phys-rev letter, which everyone in the laser field knows about, in the famous 1958 paper, in which they calculated what you'd have to do to make, say, an optically pumped gas laser, and what kind of lamp you need, and so on. This is pre-Mayman by 2 years. And they wrote this paper, and it got a lot of people thinking about the problem. There had been ideas floating before, but a lot of people, and people at Bell Labs, Columbia, and elsewhere, began trying to really make lasers as the stature of Shalom and Towns in particular made this paper. And they came up, and one of the things that they kind of threw into this was a prediction that a laser would have not only stimulated emission of the waves bouncing back and forth, but it would have spontaneous emission from each atom in the laser. And some of that spontaneous emission would go right along the axis of the laser and add to the stimulated emission. So you would have a coherent oscillator with a small amount of random noise on it. And they showed that, in fact, the laser oscillator would have a finite spectral line width, no matter how perfect an oscillator it was. And in fact, any coherent oscillator that uses a feedback and a linear amplifier would have this same line width. And it doesn't depend on anything except the center frequency of the oscillator, the cold cavity bandwidth of the resonator of the feedback loop, or 1 over the ring, this is 1 over the ring downtime, and the output power. It doesn't depend on what kind of material you have. It's true for vacuum tube oscillators and transistor oscillators as well. And they had a factor of 2 that was wrong because they somehow didn't think through what an oscillator was. They thought it was just a narrowband amplifier of noise, and didn't realize it was really a coherent oscillator it had no, this is mostly phase noise. But then recently, many years later, people realized that that if you have a non-orthogonal resonator and you go through the same sort of calculation, you get an excess noise factor greater than 1. And it's called the Petermann excess noise factor because Petermann first worked it out for diode lasers using a somewhat different approach. And then some of us realized that it was really the non-orthogonality that was involved. And so this is one experiment that some very good students of mine made, maybe around 1991. This was a very small, very compact, very high loss, very non-orthogonal diode pump vanadate laser, and we were able to show that, which meant that, sorry, the fact that it was so small meant that it had quite a wide quantum bandwidth that was not too hard to measure. And this is the Charlotte-Towns prediction, and the excess noise factor in this case was about 300, and that was in agreement with theory. And the line width was Lorentzian, as you would expect. This noise, for those of you who are signal processors, is nothing more than the fact that the instantaneous phase of an oscillator will randomly walk in phase. If there's any noise emission in the amplifier that makes the oscillator, that's going to give kicks to the instantaneous amplitude and phase of the signal in the ring, in the oscillator. The phase kicks are filtered down or are suppressed by gain saturation, but if you kick the phase of an oscillator, it'll continue to walk, it'll continue to oscillate, and if it's kicked randomly, the phase of an oscillator will walk around a ring of constant amplitude, the E field, the phase of the E field, let's say, or the phase of the signal output, and that's what you're seeing here. Okay. Well, okay. I'm trying to not run over that here, but what's been bothering me for the past 5 to 10 years is a kind of a silly question. I think you all know what Fresnel reflection and total internal reflection is. If you have a higher index medium, a lower index medium, and if you send a beam in at less than the critical angle, you'll get a refracted beam and a refracted beam going off. But if you come in at an angle beyond a certain critical angle, it depends on the energies, you get total internal reflection, 100% reflectivity. If this is a lossless medium. Now, suppose, however, that the reflecting lower index medium up here is slightly absorbing, slightly lossy. It has spectral lines in it, maybe. Then it seems pretty obvious, and it's certainly true, that there are some evanescent fields that penetrate up into the reflecting medium, but they're confined to just a few wavelengths thick here. And if this is absorbing, some energy will be delivered to them, and the reflectivity will be less than 3. Now, the most interesting thing maybe, well, I shouldn't say that, but certainly the fact that laser principle can provide us with bulk gain medium, which is just nothing more than negative absorption. A clean laser medium is just an absorbing medium, except the absorption coefficient changed sign. And other than that, it's so now we're going to have presumably there's going to be some stimulated emission caused by the evanescent fields up here. They're perfectly real fields. It's a propagating inhomogeneous wave here. Will that then, if it's negative gain, give you amplification greater than 100%, even if by only a small amount? And then you realize that if you have a fiber optic or a waveguide that has a higher index core and layers of lower index cladding on both sides, and in general the modes of a waveguide have evanescent fields that extend out into the cladding on either side, and there's gain out there, so is this mode going to be amplified? Well, if you get a TIR greater than 1, yeah, you should be able to make an amplifying fiber this way. And there may be 20 papers in the literature that say, yes, you could do this. And this was patented as long ago as 1970 something. And it intrigued me. And so I began to look into this. And I'm going to go at this a little bit indirectly. It's also the situation that if you have some kind of a waveguide or fiber, which instead of having a step profile like the one I just showed you, has a parabolic profile like this, which that means that each little section of this waveguide is a sort of a weak focusing lens, with a higher index in the center, lower in the edge. And some people call this a Gaussian duct. And it turns out that if you have a Gaussian duct like this, you can, in the paraxial approximation, you can solve the field propagation for the field propagation analytically in closed form. And you'll get a family of Hermite or Laguerre Gaussian modes that have a so-called Gaussian beam parameter. The mode that propagates down this will have a radius of curvature and I just see that something got, no, that's okay. That's okay. And also a spot size, a Gaussian spot size, and it's given by, it's just proportional to the second derivative of the curvature of the phase profile at the top. Some of you, I hope some of you work with Gaussian, okay. Okay, so now, one of the interesting things that the laser brought into this, second point is, if you take one of those ducts and it supports a Gaussian mode with a certain steady state spot size like this, and if you perturb its size or its curvature a little bit, it will go through a periodic scalloping like this. It will be over-focused and then under-focused and over-focused and under-focused. And this is mode beating between the lowest order and higher order modes of this quadratic duct. So this but its perturbation is stable in the sense that the perturbation doesn't grow, it just oscillates. Now, one of the interesting thing is that the whole basis of the whole complex paraxial optics is that you can also have a gain guiding profile. Suppose the gain coefficient, suppose this duct has gain coefficient in it or loss, and the gain coefficient, I'm having a lot of failures here. Did you have another? Got it. If you have a parabolic gain guiding profile with a second derivative G2 and an index profile with N2, this complex valued Gaussian beam solution will be the square root of this complex quantity N2 and G2. And if Actually, N2 can be 0 and you can just have gain guiding and you can still trap a wave. And some semiconductor lasers have no index guiding in the stripe in the semiconductor laser. They just have gain guiding with stripe. And also note that this Q parameter is can be the minus or plus sign. You're taking a square root, and depending on which sign you take here, you can either have a confined Gaussian beam or an unconfined beam that blows up at large distances. Now, you can in fact have combinations of gain guiding, and index guiding or index anti-guiding, and you can take a plane that would N2 along this axis and G2 along this axis, and divide it into quadrants that have the 4 combinations of guiding or anti-guiding due to gain or index. And let me just, in all 4 quadrants you get what appears to be a solution that corresponds to a trapped mode. Because one of the signs of that square root is bound to have a negative imaginary part. But if you look into this, and a guy named Lee Casperson, who worked with the RE, worked out that if you look into the scalloping behavior, essentially, of these modes, you find that the modes in these 2 quadrants up here are perturbation stable. The perturbations don't grow. And down here, they're perturbation unstable. And so you can have a beam, you can have a duct that has strong index guiding, here or here, and you can combine that with index guiding or anti-guiding, and the gain anti-guiding will always destroy the stability of the index guiding. On the other hand, you can have a beam that is index anti-guiding. This is kind of beam a Gaussian duct. This is a duct in which the index tends to bend the rays outward. But if you put some gain guiding in this, it becomes a stable and confined mode. And the short summary here is gain guiding always trumps index guiding. That's useful for understanding a lot of behavior. And so I got interested a couple of years ago in saying, well, what about if you have an index-guided step profile fiber or waveguide, and you have a step gain profile. In other words, you have a fiber whose core has a higher index or maybe a lower index, depending on the sign of delta n, and who has either gain guiding or gain anti-guiding. You have a similar behavior, and it turns out, as I'll show you rather rapidly, that you indeed have this. But this leads you back to Fresnel reflection. And I'm going to just summarize it, or show you state in a few minutes, that if you have gain in the core, you either have a Fresnel reflection of unity for all the rays at the surface here, and they're being amplified, or even if the rays are leaking somewhat in this index anti-guided fiber, if you have enough gain, you still get a trapped amplifying mode. But if you have a structure in which the core is lossless and you have unbounded gain on both sides of it, it turns out that any ray inside this launches a wave up at an angle like this, and this ray continues to amplify and carry energy away up here. And the surface interface here just acts like a lossless beam splitter or a lossless scattering matrix. You put 1 unit of energy or power in here, and if 0.1 goes up this way, only 0.99 is going to come down this way. And evanescent gain, according to me, does not exist, and it certainly doesn't exist if you have gain anti-guiding and index anti-guiding, these things. Now let me try to show you a little convincing as to why this is. Going back to the same thing I've already said. We're assuming here that this angle is steep enough that it's beyond the critical angle. So this is total internal reflection from a lossless reflecting medium, 100% reflectivity, and in the overlap region, if this is a finite beam here, you do have an inhomogeneous plane wave, which decays exponentially upward. The dashed means it's decaying, and it has a phased vector right along the surface. If you have a lossy reflecting medium up here, again you have a decaying wave, but the refracted wave never comes down to be exactly parallel, even as this incident angle goes to 0. It's always small like this, so you have a reflectivity less than 1. And the same thing in the gain reflecting case. I've been trying for about 5 years to really convince myself that for sure that was this is correct before I publish it and make an idiot of myself. The problem is I've had some superb students, and some of them have just been too good. And one of the very best students I had, mathematically and analytically, saved my neck on a number of earlier problems we were working on by coming up with the right understanding, particularly the non-orthogonality. This was a guy who understood really what non-orthogonality meant, and I didn't quite. And he doesn't believe this. So that's, that I'm still nervous, but I don't quite why he doesn't want to do it. Anyway, let's take the case of lossless reflection, and let's take a beam that's coming up like this, and I'll just stick to one to make it simple. Let's take a beam that's coming up at close to normal incidence. It has a refracted wave going up like this, and a reflected wave coming down like this. And at normal incidence from something like glass, the reflectivity is 4%, the power reflectivity. Or from a semiconductor, it's maybe 30%. So here's theta equals 0. Theta being the angle of incidence defined as this angle here. And so you have a small real reflection, and as you tilt the incoming beam more and more toward the critical angle, the reflectivity goes up like this until I picked numbers where I picked indices where the critical angle here is 45 degrees, which means that if this index is 1, this index is the square root of 2, and the critical angle is 45 degrees, and that's the point where this beam comes down and goes parallel. And if you look at what happens here, at 45 degrees, suddenly the reflectivity clamps at 100%. This is the complex valued magnitude and angle of the reflection coefficient. And you find that as you increase the angle, what happens in this plane is that it walks around in a circle and ends up down here. And I think this is a great way to plot reflection coefficients, although I've never seen it in the textbook. Now, if I had a little loss in this upper medium, and do the Fresnel calculation, if you put a little, if you have not only an index M2 up here, but you've also got an alpha 2, that means that you're reflecting off sort of a complex impedance here, complex valued impedance. You get a little phase shift in the reflectivity. So this green curve actually is shifted in phase slightly here, and more so as you go further up. There is no longer any discrete, discontinuous critical point. The critical point is just this point here, and the reflectivity does come up and becomes close to unity and goes around like this. And the more loss you have, the further this curve pushes in, as you might expect. Now, what happens if I put gain up here? Well, according to me, according to one of the, you have to take a square root in solving for the k vectors in this problem. If you take the right square root, obviously if you change the sign of alpha, you're going to have a slightly different phase angle. So the red curve is going to be a little below and the green curve a little above the blue curve. And this is going to bend around like this and go around like this, and it is less than unity. Yes?
So if I take the gain to approach 0, the curve discontinuously flips to the top.
Well, that's not an experiment that's easy to do.
Okay.
That's not an experiment that's easy to do.
So if you do it.
Well, there are better ways to do this experiment. But yeah, that was a worrisome thing. There is a solution. The other solution is one that comes along outside here and goes out like this, and then it actually predicts for lossy curves the other solution predicts that the lossy reflecting medium has a reflection greater than unity, which Bob was speaking to. That's a good question, and let me just say quickly one thing here. Suppose I come in with a beam below the critical angle, and it's going up into a gain medium. That beam is certainly going to be growing up this way, and it's going to keep growing indefinitely. And as I turn this further, this is going to bend down like this, and as I go beyond the critical angle, this is going to come down and just do something like this. And if that didn't happen, then you have to put in some kind of a discontinuity here at the critical point and jump up to a point in here and come back in. And certain people argue that that should be so, and I can't see it. Well, okay, so this is, you heard it here first. Oh, dang, okay, I'm going to quickly go on here. I'm going to have to skip over some things. And just say, suppose that I take a step function fiber with a index step delta n in the core and a step delta g in the core and lossless cladding. And so this is a conventional fiber with index guiding. If I make a laser amplifier, I put a little bit of gain in and I move up a little bit here. And if you just solve the mathematics from Salvan Teich or whoever is your favorite thing, but nobody had ever done this, you find that you have an LPO1 mode, and then at a certain complex V squared value, LP11 mode turns on out here, and if you look at the boundaries of those, they go off like this, and you can make a purely gain-guided fiber. You could have a fiber that had no gain in the core, that had no index step in the core, just a uniform index, but had a gain core down the center. You can move out to this side, and now you've got a really neat situation, because there's no purely indexed anti-guided mode here. This is an unguiding structure along here. But if you turn on the gain, there comes a point where suddenly the gain guiding overcomes the index anti-guiding, and you've got an amplifying fiber in here. And suppose you move up to some point up here where you've got enough gain that and some mirrors on the end of your fiber can start oscillating. The gain is going to clamp. You pump harder, it oscillates harder in the LPO1 mode, and you can never force it into the LP11 mode. And we have now done this. John Volato at Clemson University grew a series of neodymium phosphate glass fibers with fairly heavy doping, because you need fairly large gain, 100 to 400 micron cores, 0.3% lower index in the core here, and Mike Bass and Mark Richardson at Creole made some lasers with about 10 centimeters of this fiber, mirrors on the end. The whole thing was since they didn't have diodes to pump this, they just took a capillary tube and put this 250 micron diameter or a few hundred micron diameter fiber in the core of a capillary and pumped it with a flash lamp, just like a linear flash lamp. And it oscillates beautifully in an absolutely single mode like this. And we have made fibers that run absolutely single transverse mode with greater than 400 micron cores, which is just far and beyond what anybody else can do. Only one problem. You have to have quite a lot of gain. You have to pump that fiber quite hard. And if you just run the numbers, yeah, it'll run like this beautifully for a millisecond or so, and then if you don't turn off the pump, you've melted your fiber. and there's no way around this with glass. Some of you have got to grow us some crystal fibers with 10 times the thermal conductivity, and then we'll make kilowatt fibers, single mode in the dust. Final slide. Pardon me?
How much will it cost?
Well, people will pay a lot for those. Okay. I've told you, and I think I'm convinced it's true, fiber or waveguide with unbounded gain cladding never amplifies, and there is actually no perturbation stable mode in this case. But it is clear, and you can rally my vote, that if you have a layered gainy cladding, let's suppose you do something where we put a thin, it doesn't have to be thin, but not too thick layer of this gainy region around here, and do the same thing. This mode, this ray or this wave that's launched in here and is amplifying up like this, is going to reflect off this layer out here, even though it's just a gain discontinuity. And anything that can be launched into this from a higher index here will be totally reflecting at this corner. And then that signal will come back, and if you do this as a wave problem, you will find that in this case, the reflectivity for a finite layer is always greater than unity. So, and most of the people who made so-called evanescent lasers, evanescent lasers have done evanescent pumping. The pump wave came down this core, and the tails of the pump mode only pump the thin layer out here. And that in fact gives you, quote, evanescent gain, except that now it's no longer evanescent because you've got a growing wave going this way and another growing wave coming back this way. So it's, strictly speaking, it's not a single evanescent wave. The final point to make in the talk is what is gain guiding? Well, gain guiding is where you have, let's say, let's not plot gain, let's plot transmission. You can have no gain. You can have. I'm going to make gain anti-guiding, so I'm going to have gain in the cladding, unitary transmission, unity transmission in the core, and gain out here. If I take this, the mode in the fiber only depends on the difference between this and this, not the absolute values. It's the difference here that gives you the right. So let's take this transmission and move it down to a situation where we have lossless unity transmission. Let's see, bring this down here and have some loss. And so now this is lossless, lossless, but it's still gain guiding in sign. So if you take a fiber that's it's lossless out here and this is a faint gray, doesn't come out very well here. This is supposed to be a slightly lossy core. It does not have a propagating mode. I'm not sure that's been recognized by the fiber optic people. So that's a very fast run through of a diversity of topics, and I again thank you very much for inviting me, and I hope I haven't kept you too long.
We have a couple of minutes for questions.
Tony, by any chance, did you look at negative index refraction materials to deal with some of these same kinds of problems on low definition?
Frank, I have to say, I just can't get myself interested in metamaterials. I guess it's partly, I just don't appreciate and understand the energy flows, and secondly, I just find it hard to believe that they're going to, the answer is no, I have not found out metamaterials. Yes?
So you made a point about this, if you have an unbounded gaining cladding,
Yeah.
you should not have so you said no perturbation stable mode. So I was just wondering if you have a waveguide,
Yes.
you have basically real fields, it's a lossless waveguide first. So you have real fields, the operator is real, so if we just put a little tiny bit of loss into the cladding, you will have a propagation constant that's slightly absorbing.
And you can calculate it, if this is loss, not gain, and you have a typical field with tails, you just need to have the overlap integral, what fraction of the energy is out here, and that's the perturbation stable mode.
And so then if I just, in MATLAB, take the complex conjugate of this thing, nothing changes, I just change the slight loss to slight gain.
You're going in the other direction. You're going in the other direction. In other words, if this is lossy, the wavefront, if this is outside is lossy, the wavefront becomes conical out here. The wavefront becomes like this because the power flow is I'm saying this right?
Isn't it power flow actually
The other way.
co-linear with the wave?
No, not when you have losses. No,
A little bit upwards.
If you do a first order perturbation theory of standard lossless fiber theory, the modes to first order perturb modes, shape stays the same, but the phase tilts one way or the other depending on its gain and loss. So that supports in support of these arguments that we. And you're talking time reversal symmetry, and if this thing is unstable and going one way, it's converging.
I'm just wondering if it's a problem that it's unstable and growing because it has gain. So as long as in the waveguide you have growing power, it's okay that you have growing power.
Put the point source here, and if anybody knows how to write the Green's function on this, I would be very interested because it's very messy. But every ray that goes down here is ultimately going to leak out. So the intensity on axis is going to always decrease forever and ever. Yet the energies out here, this thing is going to be shedding amplified energy out to infinity like mad.
So if the cladding becomes anisotropic, you have to consider the non-collinearity of Poynting's vector and the ray vector, just like you do when it's absorptive. So I'm wondering if the gain becomes anisotropic as well, if that might change the story.
Well, that depends on the atomic. That depends on the atomic nature of the gain. If you're going through a gas and you've got a M equals 1 to M equals 2 transition, that's got polarization properties and so forth. And so I've done nothing but scalar wave theory and isotropic things here, because everything else is above my paper, right? No, I want to leave that for you to work on. Seriously, I'm working on it.